Let's continue looking at double integrals in polar coordinates. So we'll consider this question, convert the integral from 0 to 1, integral from 0 to root 1 minus x squared of the function x squared plus y squared dy dx into polar, and then evaluate. So I think what's going to help is to draw a picture first. So think about here we're noticing from the outer integral that x goes between 0 and 1, and from the inner integral y goes between 0 and root 1 minus x squared. Now this y between 0 and 1, root 1 minus x squared, well, this is the part that tells us, under the circle, right? So this is, if we just looked at this alone, we'd be talking about, the part under the unit circle. But then we have this additional restriction that x needs to be positive. So what we're really looking at is, instead of all of this part here, forget the second quadrant stuff, we need x to be between 0 and 1. So we actually have a quarter of the unit circle. So in polar coordinates, the region that's shaded here satisfies the property that theta is between 0 and pi over 2. And we're looking at all r values between 0 and 1. So then the given integral at the beginning is, so this integral over here is now equal to, we'll rewrite this dy dx that's right here. Let me underline this in blue. This right there is dA, and so that part down here should become r dr d theta. Okay, and if we draw our two integral signs, well, if theta is here on the outside, should go from 0 to pi over 2, and then r, dr, right? So r we see here goes from 0 to 1, and then finally this x squared plus y squared, that's up here, maybe we'll underline this in red, that down here should become r squared. Yeah, because x squared plus y squared turns into r squared. That, I guess, we could throw in parentheses just to be careful there aren't two terms there. And then let's now evaluate the integral. 0 to pi over 2, integral 0 to 1, r squared times r becomes r cubed. So we're just doing an algebra step first. And then integral 0 to pi over 2, r to the fourth over 4, evaluated at 0 and at 1. I guess when you plug in 0, we're not going to get a value. So we'll have your integral pi over 4, 0 to pi over 4 of 1/4 d theta. And so that'll be 1/4 times theta evaluated at 0 and at pi over 4. So that's going to be 1/4 times pi over 4 minus 1/4 times 0. In the end, we should get here. Oh, sorry, I don't know why this said pi over 4. Let's fix that. Pi over 2. Sorry about that. I just kind of randomly brought in a pi over 4. Should be a pi over 2. Let me correct those. Pi over 2. So we end up with pi over 8 minus 0, or just pi over 8. Let's try another. Let's look at the following. Let's integrate. F of x comma y equals root 1 minus quantity x squared plus y squared over the following region, x squared plus y squared less than or equal to 1. So this is just a way of describing the filled in unit circle, right? So this space here, just to comment on it, I mean, we're already in sort of the remark phase. The question has been posted, but this is the region, the filled in circle. Yeah. Also, as long as we're doing remarks here, let's just note that what we have for the function, the graph of the function would be z is equal to root 1 minus x squared plus y squared. And so if we square both sides, z squared is equal to 1 minus quantity x squared plus y squared. Let's add what's on parentheses on both sides, and we'll have x squared plus y squared plus z squared is equal to 1. So we're actually talking about the graph itself is, well, it's not the entire unit sphere because that wouldn't pass the vertical line test, right? But we have the positive square root. So it's actually the take a unit sphere, but only consider the top half of that. That's what we're looking at right now. So when we integrate this right here, I mean, we're talking about the shape of a sphere, but we're only keeping the top half, this half, not the bottom half. And what we're really doing here is actually, this integral, what's it really going to be finding? This is going to be the volume of R2-D2's head, right? Just a little quick Star Wars reference. Okay, so let's go ahead and set up the integral. If this region over here is called R, let's say, then we're talking about the double integral over R of root 1 minus quantity x squared plus y squared dA, but then that dA is going to become an r d theta. And see, theta, just from the picture over here, it's all the way around the circle once. So 0 to 2 pi would be fairly typical. You could do 2 pi to 4 pi, or 4 pi to 6 pi, or 3 pi to 5 pi, but I think 0 to 2 pi is probably fairly standard here. R from 0 to 1, and then our function. Well, we've got root 1 minus, and then x squared plus y squared could be replaced with r squared, like that. Yeah? Okay, so then what we're going to do here is for the inner integral, right, we're focused still on this part right there. We're going to use a substitution of u is equal to 1 minus r squared. This is going to cause us to have to update the bounds, right? Because when, for instance, so r being 0, let's just work this off to the side here. So if r is equal to 0, then u is, well, let me write this a little better. If r is equal to 0, then u is 1 minus 0 squared, so u will be 1. And then if r is equal to the upper value here of 1, then u is going to be, well, 1 minus 1 squared, so 0. Okay, so when we write this integral, we're going to have the integral, the outer integral from 0 to 2 pi with a d theta. We're not touching that part yet. But when we do our substitution and all this, this integral is going to have to be from 1 to 0, because these are now u values. There's a du here, and in the end we'll have negative 1/2 u to the 1/2 power. You got to work out a little bit of this substitution business. And then this, if we now do the inner integral, so leave the outer integral 0 to 2 pi, we'll have negative 1/3 u to the 3/2. Evaluate u at 0, and then you evaluate at 1 and subtract in that order d theta. So we'll have integral 0 to 2 pi of, when you work out plugging in 0 for u first, well, then that term drops out. And then we'll plug in 1, and now we're subtracting, but there's a minus sign here, so this should end up with a positive 1/3 times 1 to the 3/2 power. But let's not write 1 to the 3/2 power. That's just going to be 1. And let's not forget our theta here. So then, anti-differentiating 1/3 is going to be 1/3 theta, evaluated at 0 and 2 pi. The only significant value is when we plug in the 2 pi, so we end up with 2 pi over 3 for this. So the whole point is that the volume of half of a unit sphere we just computed is 2 pi over 3. Right? That's the volume of R2-D2's head. Now, what you should try, just at home, as another sort of sample problem, would be try to integrate f of x comma y equals 2 root 49 minus quantity x squared plus y squared. So, and do this over x squared plus y squared is less than or equal to 49. Now, what's this going to do? Why would you do this? Well, the 49 if you work out the details, kind of like what we had back over here, this is going to end up becoming part of a sphere of radius 7. And then the 2 is just effectively trying to say, look, if it's just going to be the top half, multiply by 2 so that you get the top half and bottom half volumes. And when you do this over the input space being the filled in circle of radius 7, this really what you should end up getting, you should get in the end, the actual volume, not half of a sphere, but now you should get the actual volume, the volume of a sphere of radius 7. So you should work that out and see, just based on standard geometry volume formulas, this would really be 4/3 pi r cubed. So 4/3 times pi times 7 cubed. And so see if just writing out what this should be and then doing a double integral in polar coordinates, in the end, do you really actually get this number?